And we are on. Wonderful. So hello everyone and welcome to our fourth session of MATLAB for image processing, and happy spring. Saturday was the Persian New Year event called Nowruz. For those of you who are not familiar, I just sent 2 YouTube links in the chat. So if you are interested, you can have a look. And it is the beginning of spring. So if you are in Aberdeen, the weather has been lovely today so far. And I hope wherever you are, the weather continues to be lovely. And today we are going to cover new things, but what did we do last session? So we went through basic programming techniques last session, including conditions, decisions, and we did loops as well. We did numerous problems and we solved them, and we started the image processing, mostly image pre-processing, and we had some exercises as well. So mainly the session was on if statements, if else statements, for loops, and while loops. But we touched a bit on image processing as well, just to start the main exciting stuff. So this session, we're going to continue what we started last session. We're going to build up on that. So it's going to be basic image processing and mainly segmentation. And we're going to do some pre-processing, and we're going to talk about processing and post-processing. And just to repeat this again, so the sessions are bi-weekly, so next session is the 5th of April. And let's go to the exercises from last session. So we were supposed to complete the MATLAB on-ramp course, and the 14th section of that has a project, a stellar motion. I'm going to open that and we can quickly go through that together, hopefully. So if you want to navigate to MATLAB Academy for that, I will send this link again if I manage to copy it, if you're not already there. So this is the link, and please, just like I am doing it now, open MATLAB on-ramp and navigate to section 14, please. So I'm going to start with the first project, stellar motion. So there is a video, I'm going to skip that, and I'm going to add a line of clearing the workspace, so we start fresh because I want to see what each line does. So my workspace is now empty. I'm going to load the data and I want to see what the data looks like. So if you open your workspace, the data is just one variable called spectra of type class, and it has 357 rows and 10 columns of just numbers. It's double. So it looks like this. Yep. So loads of numbers, large data. And there are a few lines that are already done for us. I'm going to run them again, so I have the variables in my workspace. So we have the number of observations, which is basically the number of each rows, And then we're going to look at lambda start and lambda delta, which are just two random numbers that we have. So the task is we have the spectral data collected, evenly spaced wavelengths, and you know the starting wavelength and the spacing, which are these two variables, and the number of observations, which is this one. So create a variable called lambda end, and it should contain the value of the last wavelength in the recorded spectrum. You can calculate lambda end with the equation this. So basically, we have to create this equation in task 1, and we have to use these variables to calculate a few more things. So let's start. So lambda end should look like this. Lambda start, is it capital S? Yes. Plus, in brackets, number of observations minus 1. So that's that times lambda, what was it called, delta? Yes. So that's basically our first line. I'm going to go to the next line. Use lambda n to make a vector named lambda, and it should contain the wavelength in the spectrum from lambda start to lambda end in steps of lambda delta. So we have done this several times previously. You can do this starting point, your steps, and your end point, and transpose lambda into a column vector so that it can be plotted in task 3. So we just need to transpose what we had. So if I run them, run these two lines first, so we can have a look at what lambda looks like. So yeah, did it work? Evaluate. No, it's not coming up. Strange. Run selection. Oh, there is something wrong. So what did I do wrong? Unrecognized functional variable lambda. That's the one. Okay, let's now do these. Typo. And yes, okay, so this is lambda. It has one row of 357 columns. That's why it is a row vector, and we want it to be a column vector. So we just evaluate this line as well to just transpose it. So if I submit the answers, it is correct. We can move on. Interrupt me if you have any questions, just let me know. So task 2, it is saying extract the 6th column of a spectra to a vector named S. So that is the spectrum of a star HD blah blah blah, as you can see up here. So I'm going to just create S and basically go inside a spectra and extract the 6th column. So that's that. You can submit and everything is fine. Task 3, use the log function in the same way as the plot function to plot data using a log scales for each axis. And we want to plot spectra S as a function of wavelength lambda using log scales on both axes. Use point markers, dots, and a solid line connecting the points. Add the X label wavelength and the Y label to the plot as well. So basically, just like plot, I'm going to use log. So it has to be a function of these two variables, and it has to look like yeah, dots and lines. And then we have to add labels. So X label was wavelength and Y label. I'm going to do it in one line, but I have put a semicolon, so it's not going to become incorrect. And that's that. So submit. Good, everything looks correct. And task 4. So create two variables, and we have the names that contain the minimum value of S and the index where the minimum value occurred. So we know from before that minimum can have two outputs. So one of them is the main output, and one of them is as in the minimum value, and one of them is where it is located. And we want to find the minimum of S. So that's one of the tasks completed. Use index into lambda to find the wavelength of the hydrogen alpha line. Store the result in this name. So I'm going to copy the name just to save time. And I'm going to basically index into the variable lambda and store it. So everything looks fine. This is the wavelength that we plotted in task 3. And task 5, add a point to the existing graph by plotting x lambda HA and y as a red square RS with a marker size of 8. So because we want to put the that specific dots on top of the previous plot, I'm going to use hold on, and I'm going to just plot that dot, sorry, and it should look like a square, red square with the marker size of 8. So I'm going to submit that. Oh, I made a mistake. Yes, it's a small a, sorry, typo. Submit. And everything is fine, and we have this red square as the minimum of this whole array. Next, we have to calculate the redshift factor and the speed in kilometers per second at which the star is moving away from the Earth. Assign the redshift factor to a variable called Z and the speed to a variable called speed. So we know that we can use some of these variables we had before, or yeah, they are given here, sorry. Yes, so Z is basically lambda HA divided by this number, so 65628 minus 1. So I'm just following literally this equation. So that's the value of Z. And then I want to calculate the speed as well. So it is Z times this number. I'm just going to copy it. And that's the speed. If I don't put semicolon, I actually can see the values. So these two are the results, and everything is correct. This e minus 0.4 is times 10 to the power of minus 4, and this is times 10 to the power of 2, if you haven't mentioned it before. So there is another task, and that is changing task 2 so that we look at the second star. So all you need to do, this was looking at the 6th star, 6th column. All you need to do is just to change that to the second column, and I would just submit, and everything is going to be updated, obviously, because S here is going to be used in the future functions that we have. And that's it. Any questions on this one? Please either unmute yourself or type in the chat. If not, I can move to the next project. There is a further practice thing that basically you can choose a control numeric slider for this, and you can just change the numbers. So it has to be, I think, integers. Otherwise you will get errors. And then you can choose the star as in the column that you want to look at. So this is basically showing it's useful if you want to use it. So it's between 1 and 10 if you just want to write it as a code. Moving on to the next exercise. So again, the answers are already in the folder, in the Google Drive folder. I just have created live scripts. You can just have a look at them. So this is an explanation of what happens in different stars and how the light is basically transferred down. So this is already done. We have some values in the workspace, just like the previous task. And we're just going to start task 1. It is telling us modify line 2 so that we have the speed of all the stars. So how do we do that? All you need to do is you just need to delete this part as it has told you, and it is going to basically find the minimum of all the values in this spectra rather than just that second column. So we are going to submit this. Yep, that's all you needed to do. It was already written here, which you were supposed to do. So now we need to create a for loop with a loop index called v, and the loop should go from 1 to 7 and should go through all the columns of a spectra, and we should assign those to a variable called s. So it's pretty simple. So all I need to do is to create a loop of 1 to 7 for v. Automatically in live script you get the end when you press enter, which is very useful, and already it is indented, so your code looks nice and tidy. So spectra, and I need to say just go through all these columns one by one, and that's why we have the variable called v. And I'm going to put semicolon. We don't want to see the outputs. And it's going to go through the loops, the loop, and create different variables for s. So we did that. Next one, it is telling us it is task 3. Yes, task 2 to 4 is just in this space. So now it wants us to add an if statement inside the for loop body. So we did that last session as well. And we want to do some logical indexing into speed and to see if it is equal or less than 0. We want to see a log plot. So I would literally just copy and just paste it here, because we are going to just modify this and create an if statement here. So all we want is that if the speed, that specific speed in that loop, is less than or equal 0, we want to see a log plot of lambda itself, I think, yes, and s, and it has to be dash. Yep. Now it is telling us add the command hold on between the two end statements so that the only one plot is created. We don't want 7 plots because we are doing 7 like iterations of the loop. So I just need to add one hold on here, and when it goes through the first loop, it reads the hold on and then continues putting all the other plots on top of that. So if I submit that, then we're going to be able to see the plot somewhere as well, hopefully. Yes, there it is. I had the workspace open and now things look weird. Sorry, so many applications open, it is slowing down my computer. There you go. And then if I carry on to next task, again, we want to add something to the previous for loop. So I'm going to literally copy that, paste it. And now we want else here. I think, sorry, it goes after log. Am I right? Yes. Okay. And we want to see if that condition, as in if speed is not equal or less than 0, we want to see a different type of plot, lambda s, and it should have a line width of 3. So that should be it. And then we need to add a hold off after the for loop is completed. So later on, if there were other tasks, which there are, we don't plot things on top of this plot. Now, if I submit this, we're going to, there is something wrong. What did I do wrong? Does a plot with 7 lines exist? No. So S is a spectra. If it is less than 0, this should be double quote. And lambda, I'm just checking the spelling. I probably have missed something. And line width of 3. Am I doing anything wrong? Let's submit again. No. Ooh.
Is it bothered by the first loop that you've still got there?
Yeah. So let's comment these. So first loop, what's happening? V is 1. And then speed is less than 0, lambda. Everything looks fine, doesn't it? Let's submit again. Strange, sorry. Good, okay. I should have just commented these out. So potentially in the answer script in our Google Drive folder, those are uncommented. So step by step, just comment other bits out and run them. Yeah, good. So let's move on to the 5th task. Add a legend to the plot using the array star names. So star names is already there. So instead of actually typing a string, we can just use star names. Am I right? Yes, okay. And that goes through like all the strings inside the star names and just uses those as the legend for this plot, the log plot. Now we want to create a variable called move away that contains the elements in star names that have a speed of more than 0. So anything that is positive has to be moved to a new variable called moveaways. And everything is correct. And you can go through the further practice as well. Any questions on this exercise before we move on? These were easier than the other exercises. I think. Good. I will exit the course and keep this page open. We are going to need it later. Wonderful. So let's go back to our slides. So as a reminder, we covered some basics of image processing, including like a few very useful MATLAB tools, MATLAB functions. One of them was size. So we discussed that if we have a color image, normally they have 3 dimensions, and the 3rd dimension is referring to RGB colors, and you can index inside those and extract each color plane individually. So for example, you can just look at the reds, or you can just look at the greens. And basically, if you have an 8-bit image, which normally is the case, you have 256 different intensity values. So basically, it ranges from 0 to 255. We covered grayscale images, and we discussed that they are easier generally to deal with, easier to code. It takes 1/3 of the space required for an RGB image, color image, and they require less computational power to process and can reduce your computation time as well. And obviously, developing an algorithm is easier for them. Then we talked about increasing the contrast and darkening the darker pixels and brightening the brighter pixels. We did a few examples of that. And we talked about different things that the app ImTool can do for us. So that literally does all of these in one package. So today, I'm going to mainly be talking about image segmentation. Segmentation is the process of dividing your image into different segments, different parts. So it can be sets of pixels, and they call them image objects as well. So I will give you an example in a few minutes, and we can talk about it later. So this basically simplifies or changes the representation of the image to make it easier to focus on those bits of the image that we are most interested in. And it is used to locate the object boundaries, so if you have lines or curves in the image, and it has a lot of applications, so it is used a lot. So if you want to do content-based image retrieval, machine vision, object detection, recognition tasks, traffic control systems have that, video surveillance have that, and most importantly for us, medical imaging has that as well. So we want to have the volume rendered images from computed tomography, for example, if you're doing CT or MRIs. So we want to divide our image into the useful bits and just put aside things that we don't need. And when we complete segmentation, we're going to have a label assigned to every pixel of the image, and that basically tells us and tells the computer what labels we want to focus on mostly. So when it comes to medical image segmentation, the aim for us is to study anatomical structures most of the time. And basically in MRI, it is used mostly, not just these, mostly for measuring and visualizing the brain's anatomical structures, as I mentioned, analyzing brain changes, delineating pathological regions, surgical planning, and image-guided interventions, because it is basically, as I mentioned several times, focusing on those areas of the brain that we want. For example, if you just want to look at gray matter, white matter, CSF, just the bones. So you can divide, for example, one MRI image of the brain, of the head, to just have different sections of that. And there are different techniques involved. So basically we have threshold methods, edge-based segmentation, region-based segmentation, clustering-based segmentation, watershed-based methods, and artificial neural network-based segmentation. So that's basically machine learning, and a lot more. So it's not just one method, and you need to know like which methods are best for you to use. So let's open MATLAB and go and start do some segmentation. So I'm going to have my MATLAB open. As per Martina and Julia's suggestion, I'm going to start a live script this time so that we don't have so many images open. Last session we did that. So I'm going to save this live script as, where are we? Yes, we are here. And I'm going to give it a name called script session 4. Oh, 4. Good. So I just created a live script and now I'm giving it a name, saving it, and we can start. So in live script, you have, as I mentioned before, you have the option of having text. So I'm going to say this is session 4. You can edit this and choose different types of topics, headers, headings, and this and that, or have normal text, or just have code. So as I mentioned, there is an image that I already have shared on the Google Drive folder. The link is in the chat. Please download that and put it in your current folder. So that's the image. It is called 1JPG, and it looks like this. So it is a receipt that I received from this garden center called Dobies in Aberdeen. So it is a full receipt, but I just selected, like took a picture of it using the camera that I'm looking at the moment. And it's just the top bit. So it doesn't even have what I bought, but yeah, it does the job. So let's start working on that. So as I mentioned, the image has to be in your current folder because we're going to load that and then use it. And we have saved this script in the current folder as well, so MATLAB is not confused looking for things. So I'm going to start fresh, so clear everything. Everything is clear, but just to start fresh, closing all the images, clearing the workspace, and clearing the command window. Let's load our image into our workspace. So I'm going to call this IMG for just image. And we discussed that IMRIT is used for loading the images. So I'm going to just simply load that and run. So as you can see, it's a matrix, three-dimensional matrix, size 720, 1080, and 3. So the last 3 refer to the RGB planes, and we have 720 rows of numbers, 1080 columns of numbers. So it's quite like large on memory. And let's see it. Let's see how it looks like. So imshow image, and you can see the output any minute. Yeah. As I mentioned, it's just this receipt that I'm holding, and it's just the top part of it. And you can see a bit of background, which is our lounge, and this is my arm, so it's in the picture as well. So we're going to try to, throughout like at least half of the session, most of the session, we're going to try to focus on the receipt and try to do some pre-processing to see if we can get a good idea of what is written on it, so we can use the text later for further analysis. So that's how it looks like. First thing, as we discussed last session, is to create a grayscale image from this color image, because it makes our life a lot easier. So the function is into gray, and the input is image. So I'm going to create that, and then if you want to have a look at it, I called it GS. No, GS. Okay. And now if we want to see it, you can press run, and it should show both images. So there is a color image here on top. I'll make it smaller so we can see the outputs. And this is the grayscale version of it. As I mentioned in the slides and last session, the grayscale is a third of the color image because we have only 2 dimensions. We don't even have these anymore. So it is turned into a grayscale color image for us. Now, we did this intensity adjusting, so I'm going to call a new variable here. I call a new function here and put the output in GS adjust because we want to adjust the intensity using im adjust. And then we want to see the output as well, so it is called GS adjust. And if I run it or run this section, it is going to go through lines. You can see which lines it is it's going through, and then we can see the output. So this is now the adjusted intensity image. So it looks obviously a lot better already. It's more visible. We can see the text. I can actually read some stuff, and I can't read, well, I can read them, but it's not really nice. So we discussed that one way of pre-processing our image is using thresholding. So we know that there is a range of intensity that this image has, and we can basically index into those intensity values and just select a portion of that intensity. So that's what I'm going to try to do. So I will create a new variable called BW, and I will just select a third of maximum. So this is 255 is the maximum intensity. So I'm telling MATLAB that I just want to select basically from 1/3 upwards. So any intensity that is more than 255 divided by 3. So I'm going to do that, and let's see the output. Let's see how it looks like. So MATLAB is going to logical index into GS adjust and put the output in BW, and then it's going to show it to us. So let's see how it looks like. Okay, so basically it looks like this. Do you think we should change this logical indexing? And if so, what do you think we should put it at? So let's just try a few values. If you have a good number, just let me know. So I'm going to do GS adjust. So this is, I think, 85. Yeah, 85. Let's go 100 and see what happens. Okay, the 100 looks like this. We still have background, and yep, we still have some stuff. If I go lower than 85, for example, 50, what happens? Okay, so this is 50. Yep. Sorry, I'm just showing G-adjust. I should show BW. Sorry, it should look different. I go 100 again. So we see 100. My bad, sorry. And let's see 100. And the output looks like this. So we have some stuff here, a corner here. It looks obviously different. And if I go down to 50 and run again, it is going to look like this. So the background is now bright, so we can't really differentiate. You see some of my arm. Okay, so we know that we are changing, we are indexing into intensity. One way that we were doing it last session was to use im tool to get a better idea of how that intensity looks like. So let's just go to im tool and see if we can find out what is the best intensity range to look at this image. Any questions so far? I'm looking at the chat. If anybody has any questions, you can unmute yourself or just type in and I will just pick it up. So this is my im tool window. First, I need to import the image, so I can just open the image externally, or since the image is already in my workspace, I will just choose this. Or is it BW that we are adjusting? Oh, GS adjust. Okay. And then there were different things you could do. This is just getting more information about this image. Yep. So this is the information. It has the width and height of these numbers. It's an 8-bit, and maximum intensity is 255. And then this is basically the intensity value. So if I want to basically tell it, just focus on, for example, these bits. Yeah, 100. And then from here, go down a bit as well. Good. So as you can see, I'm just trying to focus on the receipt itself, not see the background, and just see if I can have the text on the receipt visible as well. So as you can see, it's like around 119 to 246. So now if I close this completely, and for example, now have a range of 2 values. So I can say anything more than 100 and less than 240. Let's see how the output looks like. So we are still using the thresholding. So we are trying to threshold our intensity and see if we can get a good output out of it. But as you can see, the output of thresholding is not the same as im tool, is because im tool is using different algorithms to do that. And we are not, we're just literally thresholding the intensity. So you can do this thresholding for RGB color images as well. And you can create masks for each of those 3 colors. So if I had a color image, which I do, you can do this for red, green, and blue as well. Or you can just threshold using a combination of these. So you can have differential masks, as in, for example, red minus green should be more than this much. So if you after this session, or if you have already done that, if you have seen image processing course, not the on-ramp image processing course, that gives you a good idea of how different combinations of thresholding can be used for different images. So I think the image processing course is using an image of strawberries or a number of different fruits, and then you can actually do the pre-processing that we are doing to find out which strawberries are ripe and ready to be picked. And another thing that is mentioned in the MATLAB image processing course is that you can convert your images between RGB and L star, A star, B star. So these are two different modalities. If you are interested, go to the MATLAB website and look for RGB or L star, A star, B star lab. And find more information, or complete section 4. It is section 4 that is mainly talking about segmentation and thresholding for image processing course. So we leave this to that. Now let's try to threshold the intensity of the grayscale image automatically. So this was thresholding manually, but there is another way that MATLAB can do thresholding, and that's, let's start a new text and say, let's try to threshold automatically. And let's code it. So that's called binarize, the function that we are going to use. So we are going to generate a binary version of our GS adjusted image. So how does it look like? I'm just going to show you how, when we turn this image into a binary image, the image is going to look like. So that's now done automatically. So as you can see, it's still not good. And if we wanted to basically decide on like the best techniques of doing this segmentation, it's still not doing the right thing for us. But there is a second input that we can add to our binarize function, and that's doing adaptive analysis of binarizing. So I will create a new variable called gbinary adapt, and instead of just leaving the binary input like that, I will just add adaptive to this. Okay, now let's see both of these images, the binary images, next to each other. Binary, just to see if there is any difference really. Adapt and next to each other. Good. I will run this section. Good. So there should be a final image here. Fix typo. G binary instead of GS binary. Good, so the difference is now, this is the normal binary and this is the adaptive binary. But again, it's not really good. So we are trying to basically create a mask, as you know what we are trying to do. We are trying to create a mask to get to the useful information and remove whatever we don't want. So if we set the foreground of the image to dark and the background of the image to bright, it might look better. So let's try that. So let's create another variable, or just update our variable. Again, binarize has another option. So GS adjust and adaptive. Now you can basically tell MATLAB that, sorry, this is hidden. Yes, I want the foreground polarity to be either dark or bright. So I want it to be dark. And then if you want to see it, I will press a few lines so it comes up a bit. So basically, this is what I have done. This is the line. I just added these two extra inputs to our previous command. And if we now look at it next to our adjusted image, automatically adjusted, it should look slightly better. Save. And ooh, something is wrong, sorry. So we're using, what am I doing wrong? Foreground polarity, adaptive geosuggest. These are fine. It is here.
Do you need IM show pair?
Oh, sorry. Correct. Good. Thank you. So that is now going to show a pair of images next to each other. Wonderful. So this is the output now. So as you can see, the text is quite visible. We have a bit of background, which we still need to get rid of. And we need to make our image a bit more visible. Now, another way to improve the visibility of the image is to look at the number of ones in each pixel row. So we know that our images consisted of zeros and ones. So if we plot the sum of each column or each row of our image, we will find out how many ones and zeros are in that image. So that's if we are doing, if we are trying to look for the text, which we are at the moment, we are looking at this receipt, the pattern of where there is a text and where there isn't should be different from each other. So let's find out the number of ones in our binary image. So we are trying to find the number of ones in each pixel row. So I'm summing all the values in the row by telling it to do this 2. That's telling it to go to the row. And then if I plot that, I can see the pattern of my image. And that gives me a better idea of how I can basically play around with this visibility. Of note is that when we look at this image, the plot, you can see a lot of peaks, and basically it is fluctuating. And this is the norm when you're looking at a picture that has text in it and there is nothing else. So there is text and then there are gaps between text. So when there is a text, it goes like up and down, and there is not, it comes down, text, not, text, not, text, not. And that's how basically it is. But when you have an image that doesn't have text, it doesn't have this pattern. So basically, by looking at this, you can remove those bits that don't have anything meaningful to you. So you can just ignore that. But since this is just going up and down, we just keep it as it is and try more things. So in case your image is noisy, you need to do noise removal and some other pre-processing bits. So let's go back to our slides, if I can find them. Good. And talk about what happened. So we use thresholding to create these masks by logical indexing into our variables, our intensity variables, but it wasn't really good, the results. And then we looked at the intensity histogram, and we tried to like adjust for that by just doing thresholding. It became better, but it wasn't still good. Then we did the thresholding automatically by creating binary images. But you need to be careful with that, because we realized that we can use other inputs such as adaptive and select appropriate foreground polarity, which was either dark or bright. So when we use binarizing in binarize, it is actually calculating the best threshold for your image, but manual thresholding might still be better, because in binarize uses a global threshold for all the pixels in the image. But adaptive fixes that and improves it sort of, and it uses the best threshold for every region. So it looks at smaller portions of the image and does the binarizing. And by default, foreground of an image is assumed to be bright, and the background is assumed to be dark. But for receipts, the foreground is dark and the background is bright, and that's why we chose dark. And then we did the sum to find out the number of ones and zeros. So rows of pixels that have more zeros values are normally text, and the ones that have ones are basically blank. Therefore, you can use sum to find out more information about your image. And images without text, as I mentioned, they don't have a clear pattern. So it's like one line going down or a different pattern. It's not like going up and down. And background artifacts distort the pattern as well. So that bit that has my arm in it, that's the background. We don't need that really. So how do we improve our segmentation, our pre-processing? So basically, we want to convert the images to grayscale and adjust contrast, which we already have done. So that's called pre-processing still. But we need to do some more steps, among which we have noise removal, removing the background, and morphology. As we go ahead, I will talk about these. But basically, noise removal, it creates smooth pixel intensity values in irregular pixels to reduce the impact of variation when we do the binarization. And it basically is a filter. So it is filtering your image, and it's getting rid of those irregular points in your image that you don't need. And you can use different techniques to do that, and we are going to go through that in a bit. And then we can remove the background, which is basically isolating and removing the background before binarizing. And morphology is emphasizing particular patterns on particular patterns or shapes in a binary image. So what time is it? It's 3:05. Shall we have a break of 10 minutes, let's say, and we come back at 3:15, or are we good to continue?
Quick break sounds like a good idea for you.
Wonderful, wonderful. Let's come back at 3:15. And if you have any questions, I'm here. I will answer questions. Great. So I will just check again to see if my microphone is working.
Yep.
Yep, everything is fine. Great. Good. So we're going to try to do some noise removal now. This is basically done via filtering. So MATLAB has different types of filters. If I can show you this page. So this is basically one of the things that we are going to be doing. So there is a function called fSpecial, as you can see, and there are different types of filtering that it can do. So like averaging, average filtering, disk filtering, Gaussian filtering, Laplacian filtering, log filtering, motion filtering. So it does all these different types. And there are examples. So this is one of the very famous image processing pictures that is always used. And you can see how different filters work on it. So when you do filtering, normally, as you know, you're creating a blurry image with useful information. So we're going to now start create an averaging filter of a certain size. So I minimize this too quickly. So so if you look at this, so this is the one that we're going to use. So we are going to use an average filtering of a certain size. So for us, it's going to be a 3x3 filter. So all we need to do is to create that filter and then apply it to our image. So I'm going to create a new variable called field for filter, fSpecial, and it's the type average. And size is going to be 3x3. So all you need to do is just tell it it is a 3x3 matrix by just putting this number. Or if you wanted a different size, you can just specify the size in square brackets. So this and if you just leave 1, 3 here are going to be the same. So I'm just going to do that. But you can use different shapes of this averaging filter and basically filter your image. Now let's apply this filter on the adjusted image that we had from before. So I'm going to create a new variable called GSSmooth. So I'm going to basically create a smooth image, a filtered image of GSAdjust. So imFilter is the function that we use to implement the filtering, to apply the filter. And I'm going to say my input is this, and the filter that I want to use is called fields. So that is now filtering my image. Just this line is filtering my image. So all it's going to do is to basically put the image here and just put the filter through all the pixels, and it's going to basically have a neighborhood and filter them based on the average of the intensity of that neighborhood. Yeah, my computer is pretty slow with MATLAB. Apologies for that. Yours might be finished by now. So there are ways of improving this filtering. I'm going to try to see if I can show you the filtered image at some point when this is finished. Sorry, it's taking forever. Good, it's done. And if I manage to do show GS smooth. And I will just run this line rather than running everything. Then it is going to look like no, it's very slow. Let's see if I can open it here. Good. So this is basically what the filtering has done. So if there was any noise in my image, it's going to remove those noise pixels automatically based on the average of that 3x3 square filter that we created. So in order to improve this, there are different things you can do. One of them is to improve out of border pixels, and that is running. I will just modify this, adding another input to this. So it is going to be replicate, and what replicate does is basically trying to remove. So this is in filter. I've just opened the page to show you what other options you have. So if you go all the way down, you can see that you have symmetric, replicate, circular, and each one of these does something. So I'm trying to basically apply this replicate thing to remove the unwanted dark outline of the binary image border. So that's what it does mainly. So now if I evaluate this and do this, my image is going to look like this. So it is slightly improved because the borders are going to be better shown in the image. So I would do close all, so I close the images. Good. Now, if these are done before we do the binarizing. So now if I binarize my image, just like we did before, in binarize, GS smooth. So this is now the new one that I have, and I'm going to use all the inputs. So it was dark. I'm just going to use this, set this to dark. So this is the binarize that we had previously. I'm going to drag this a bit here so you can see the line if you're typing from the screen. And if we look at it, it's going to look like this. So as you can see, it looks quite nicer now. So now we have like a differentiation between what is text and what is not, but we still have the background, so we still haven't completed the pre-processing. If we could get rid of like these areas or do something about it and just have the text visible, and even better visible, because this is, for example, the transaction number, but I can't read it. The staff name was Jesse. So yeah, there are some things that are quite visible, some things that are not. That's why we have, excuse me, that's why we have background removal. So I'm going to create a new section and call it background removal. So in order to do that, just like the filtering, we need to create something. So that something is a structure. And here I'm going to use a diamond structure. So it looks like a diamond. And I'm going to basically use the built-in function called strel and say create this diamond shape of distance 5, and that's going to be the structure I'm going to use to remove the background. So if we there are different ways of doing it, but I will just mention the name. So if we are now going to apply a closing technique to emphasize and connect a brighter background, and then we can remove the thin dark lettering and then have that mask ready. So let's see how it works. I'm going to apply this. Because it was using closing technique, I will call it GS close. I will explain what this means though. And basically I'm going to, just like in filter, you're just telling it to apply this filter on this image. So this is applying this on that image. And then we can have a look at GS close. So let's run these lines and see how the output looks like. Wonderful, we are getting there. So basically, this is closing our image. So it's trying to basically remove this background. And as you can see, it is sort of removing some of the main parts of the image as well. But it's not really that good, is it? No. So let's try different sizes. Let's change this. I just chose 5 as the D of the diamond. Let's go up. I'm just giving it a random number. So I'm trying 20 now, just to making it a larger portion. This is it. Okay, so this is the output. Now, basically, this is trying to just focus on the background. So then we can take it out of the image. So we are creating a mask of the background. So it looks good because we have the image as white and we can differentiate these background parts and try to remove them later on. So if we want to do that, we have to subtract the smooth image from the background image. And I'm going to store it in, I'll enter a few lines so this comes up. I will store it in a variable called gsub. So I'm trying to subtract the smooth image from the close image. And then let's see that. So this is basically going to be our background removing step. GS close to us. I have a lot of typos today. Wonderful. So this is the way it looks like. So this is sort of trying to focus on those pixels that we wanted to remove, but it is sort of inverted. So if we want to basically see the text in dark pixels and the rest in whitish pixels, bright pixels, we have to invert that. So let's invert it. Sorry, I'm opening new figures again just to make it faster, because if I run it within the live script, it's going to be pretty slow. So I'm going to create a new variable called this, and then I'm going to binarize that as well, because we did all of these before binarizing our image. So these are the, again, pre-processing before binarizing. So I'm binarizing that image and I'm inverting the intensity. So whatever is bright is now going to be dark, whatever is dark is going to be bright. And then let's have a look at the output. So this is now going to look like this. So again, most of the background, the unwanted parts are removed, and I have more or less a good amount of text here. and it can be still improved, but well, it's not that bad either. So basically we created the mask, we removed the unwanted parts, and now we have the text. So these last few bits that we did are can be done using a technique called bottom hat transform or bottom hat filtering. And there is actually a built-in function, a MATLAB built-in function for that, which is, I will call it gbot invert because it is bottom hat transform. And the function is called inbot hat. If I don't have typos, yes, this is correct. And you can basically tell the function that I want to apply that structure that we created. So this structure for removing background on my GS adjust image, on the adjusted intensity image. And basically it does all of these. So it does the closing and stuff for us. So we don't need to do those. I will show you how it looks like in a second. And again, so this is the dark image that we had, and then we inverted it to get the right intensity. Another way of doing the intensity inverting is using, I will just save it in gbot hat variable, is using a built-in function called image complement. So image complement is going to go through your input, which for us is gbot inv. Yes, it's going to go through that, and it inverts everything. So if it's a 0, it's going to be 1. If it's a 1, it's going to be 0. So basically the intensity is going to be inverted. And if I now try to see that, gbot hat, that is going to look like this. So this is the one, and as you can see, it looks slightly different from the manual bit that we did, but this is what the bottom hat transforming is basically. Good. So let's go back to our slides. You can lean back and relax now. This was the coding part. So I'm going to explain what just happened. So we used ImAdjust to improve the appearance of our image, and it was useful because we wanted to do that to improve the performance of our processing algorithm as well, but it wasn't enough. So we introduced spatial filtering to smooth our image. That was the noise cancellation, noise removal basically, to remove noise and any unwanted detail. And obviously it again helps with our processing step to produce better results. We can remove the background to get rid of the unwanted information using in-top hat. In-top hat inverts the intensity, so then we used in complement function to invert it. So if you look at this image that we have, this set of images that we have, so we had an original filtered image, and we created a mask of the background by opening. So this is using an opening technique to do that. I will explain these in a bit. And that's how we basically managed to get rid of the background, basically. And when the background is dark, you can use the top hat filtering, which we explained, for background subtraction. And it literally works just like that. So you're subtracting the background, just like the name. And the neighborhood needs to be large enough to include a bit of background when you're covering a foreground object. And first you need to estimate the background. So you create a mask of your background, and this was done by either closing or opening, which I'm going to explain. And by opening, you are emphasizing on darker regions. So in this image, you're emphasizing on darker images. By closing, it's the opposite. And then this was the break. We already have had it. And apart from these things that I explained today, you can do a lot more to improve your segmentation. We didn't get the perfect image from our pre-processing procedure. We wanted to literally have just an image of this receipt so that we can basically look at the text and do some text mining, or just add up like these things that are inside and just do some calculations. We didn't get to that point that our image would be perfect for processing, and that's okay. We can use different things to basically improve our segmentation, improve our pre-processing. So there are methods that are mentioned here. So we have some cleaning functions to remove a stray noise from a mask. So sometimes when you look at a brain, most of you are doing brain imaging. That's why I mentioned brain. When you look at a brain that is already filtered, you still see like bits that are even outside this skull, and those are the things that you really don't want to see in your image. We can use morphological operations, which are basically shape-based filtering. And this is replacing the pixels in your image by a minimum or maximum of a whole neighborhood. And some of these methods include erosion, dilation, opening, and closing. So please have a look at these if you want to find out more information about them. We used closing in the example. In the breast cancer image, we used opening. If opening was used, we didn't do it. It was already done. And there are many other techniques to improve your pre-processing, specifically segmentation. So these are all covered in the section 6 of MATLAB image processing course, the main course, not the on-ramp. So most importantly, there is actually an image segmenter app that you can use. And let me see if I can find it in the app part. It is called segment something, if I remember the name. Sorry, I should have written the name somewhere. Yeah, image segmenter. So this is the app that you can use, and you give it your GS adjust. For us, it was in the example, your adjusted intensity image, or even your like original grayscale image, and then you can do all of these things that we did, and it has like, let me actually open it and I will show you what it has. Yep, so it opens in a new window just like we had before, and then yeah, you can load your image. I'm going to load something from the workspace. So for example, we had GS adjust, and it is asking me, would you like to increase the image contrast? If so, image segmenter. It is going to even adjust it itself. So I'm just going to say yes and load it. This is just to literally show you what this is capable of doing. So you can create different masks. So we did thresholding sort of, where you can do all of these things. So it is literally like those apps that you have on your phone, and you sort of do different things before you post it onto Instagram or something. So this is going through those basically, but in a bit more detail and more professionally. And you can basically add different things to your mask. So you can have regions of interest. So for example, my regions of interest would be literally this receipt, the whole thing. And then you can just remove the rest of it from the mask. So it creates a mask of what you want or what you don't want, and then you can use the rest of it. And you can refine your mask by these techniques that I just mentioned. So these are the morphological ones, and you can clear borders, fill holes if there are holes. You can invert your mask. So this is the yeah, there was a name for complement function that is basically inverting your intensity. So there are different things you can use, and then you can export your final mask to your workspace and use it and save it for future use. So for us, if you are doing pure image processing, so you have literally like an image of receipts, or you're trying to do text mining, or you're trying to do like traffic control systems. So you're focusing on certain things in one image, and you're trying to basically label those. But how does it work in brain imaging? Because that's what we are mostly interested in. So pre-processing normally involves different steps, and it's one of the very important parts of your data analysis. I don't want to say it's the most important part, because it might not be, but depending on what you want to do, what your processing involves, it's very essential that you do the pre-processing correctly. Just like, for example, when you're doing machine learning, the pre-processing is really, really, really important. Cleaning your data and then preparing it for use for your algorithms is literally the key. You spend so much time on it, and it has to be done perfectly. Even some parts you have to do manually. You can't do it using a built-in function on an algorithm. So it's very essential. So these are some of the things that you do when you're pre-processing your brain imaging data. So you import your DICOM images or nifty images if they are nifty. So they can be 4D, 3D, then you convert them to something more meaningful. You can realign them if you have a group of images, which you normally do. You normalize them, you smooth them, doing filtering basically, which we covered some of it in this session. Then you do segmentation, which again, we did some things about it, and you do warping, and you basically do averaging your anatomical images if you have, for example, a certain type of disease that you're looking at, or a certain age that you're looking at. So all of these can be done in SPM12, we know that, or in FSL. So you do all these steps. But in segmentation, which was the main topic of this session, mostly about pre-processing was, but segmentation, you want to basically figure out which parts of the structural image belong to gray matter, white matter, CSF, bone, soft tissue. So basically you have the image, and you have the image, and you want to basically label everything you see in it before you start your processing. So if you're interested in CSF, you just extract the CSF. The rest is a mask that you're just removing. Or if you're interested in gray matter, most of the time you just extract the gray matter, and the rest are your compounds, and you just remove them. Let me actually play this video for you. So this is a SPM 12 tutorial by Justin O'Brien. Hopefully you can, you can see it. I'll maximize. So this is basically after the segmentation is done. I'm just trying to give you an idea of what happens. So I think I put the speed a bit faster. I would just put it normal so actually we can understand what he says. Good.
We're not hearing his sound, Amir.
Oh, sorry. I thought you were going to. Let me see. Thanks for letting me know. This doesn't work without sound. If I set this to internal. I will put a link of this on our chat. And show conversation. Sorry, last time I played the video, the sound was there. This time, I have no idea. Paste. So this is the video. And I'm on, oh, I can go a bit back. Yep, like 11:06 should be fine. I will wait for everyone to open it. And I will try to see if I can change my sound settings so you can actually hear this. I will play again. If the sound doesn't work, you have the video. So yeah, basically when you do your pre-processing and your segmentation, you want to see something like that. You might not have as many labels as Justin had, but basically you can do all of these, and this is like a very complete segmentation. Unfortunately, I don't know if we are interested in covering like all of these pre-processing and processing steps in SPM. If you are, please let me know, and that would be a very quick, potentially 1 or 2 sessions that I would just quickly go through the GUI, the user interface of SPM, just to show you like basics of pre-processing. But if you are mainly doing image processing, these are the basics of image processing. So I would really appreciate if you complete the image processing on RAMP, which you are able to now by the end of the session. And of course, you can proceed with the image processing course as well. But again, just to repeat that, it's mainly on image processing. It's not on like brain imaging or anything. It can be used. The techniques are very similar. So we touched on some of the stuff that are actually used in the algorithms that are behind brain imaging packages, software packages, but they are a bit more different, advanced, or different, just different. And basically, except for choosing the necessary settings. If you are doing the pre-processing or segmenting your images, leave everything as default. You just choose your images, you import them to the package, and then you just select the options that you want to change for segmentation on SPM12. It's not that complicated, but you need to be very careful with your segmentation. You saw that the images that Justin showed us were really nicely segmented and warped and everything. So the pre-processing was really good. But it's not always the case. So we have very bad data as well, that you can't get things working as you want them to. So as I mentioned, we touched on basics of image processing. Sorry, it's a vast area. So we can't cover everything in 2-hour sessions. MATLAB sessions are actually 3-hour sessions in universities, but it's a bit of an overkill for this course. And it's not that we need all of these things. Most of these things were to just give you an idea of what is behind an image processing like procedure. And you can finish image processing on RAMP now, and you can complete the first 4 sections of image processing main course if you have access to those. And of course, you can finish the whole image processing course. I will show you if I can share this again. No, wrong one. No. There is another one that is open still. Yeah. So if you go to image processing on, this is on RAMP, we have finished that. If you go to image processing with MATLAB, as you can see, I have just gone through to get material for this, but it has wonderful examples. For example, you have the glacier images from 1980. You can compare them to 2011 and see how much ice has been melted. And you have images of coins that you can classify. You have images of receipts you can classify, mainly in MATLAB on RAMP, image processing on RAMP. You can do like the strawberries that I mentioned, fruit classification based on color. So it's very interesting, and you can learn a lot, like what techniques are involved in pre-processing of the images. And obviously it is very useful if you're using pure image processing for deep learning or machine learning, as in your next step is deep learning. You need to know how to do the pre-processing of your data before you move to that step, as I mentioned. But there are other things like analyzing texture and analyzing objects, detecting edges and shapes in the image. So for example, if you have circles like coins in your image, how would you detect those? And how would you differentiate between them? And for example, for coins, you can have different coins in one image and add them up and see how much money you have just from the image. And it teaches you batch processing. For these sections, I would recommend that you finish the fundamentals, the MATLAB fundamentals, because that would teach you more advanced programming techniques that are potentially required in this course as well. So finish MATLAB on RAMP, finish fundamentals, finish image processing on RAMP, and then move to image processing, the main one. And basically, it has other things that you might be interested in or not, like geometric transformations and everything. But I don't think they are relevant for what we are here to do. So if you think you want me to add one very brief SPM pre-processing at least session, or just touching on processing as well, I can ask even Gordon to do this. He's an expert in this. So if you want me to do that, we can have that. But I think at this point, I will close image processing. Next session, if Julia and Martina are here, I didn't see their names in the list of attendees today. But next session, I think we will move to machine learning, and then the following session is going to be deep learning. Again, it's going to be briefly touching on these topics. It's not going to be really like in depth, but you will have the basics to carry on from there. And again, you have now the basics to carry on image processing, whatever you want to do with your images, if it is not like using SPM. I will create a survey. I will spread it around. Everyone can just participate and let me know if you want that SPM session, and we can have that after the machine learning and deep learning sessions. Otherwise, I think we just have 2 more sessions to go, and then you are free from me, at least. You won't hear me anymore. But yeah, the next 2 sessions are going to be taught and moderated by our MathWorks colleagues. So Julia and Martina are going to cover those. I'm just going to be there if there are any questions in the audience, in the chat. I will just try to type things in and not interrupt. And thank you for joining us. This is our 4th session. I hope you enjoyed it. Sorry again if it is very brief and if it's just touching on things. I hope you find it still useful. But again, there is a lot to discover when it comes to image processing. But yeah, I hope you enjoyed it, and thank you for your time. Thank you for joining us, and have a lovely rest of the day and rest of the week. Thank you.
Hi, Amir.
Yeah.
Hi. I have a question, please.
Yeah, of course.
Thank you. I've been doing image processing for rat brain.
Yeah.
And there is a function for the affine transformation in MATLAB.
Yes. Yes.
But when I do it, it do more of deformation.
Yeah.
Do you know why, and if there is other better functions?
Yes. Could you send me, please, your image? It depends highly on the image that you have.
Yeah.
And let me close this, stop the recording, and then we can talk about it.